Right, now I'm ready. Thank you for your patience, and then let's start lecture for today. Today we will learn about the software security. So we will mainly focus on the buffer overflow vulnerability in detail and then exploitation. And then we will learn more about how we can use testing tools to find this kind of vulnerability later in the coming lecture on the 2 weeks later. But today we will focus on the buffer overflow vulnerability. And there are two important things to announce. So the first thing is that we need to reduce the due date for the NSA code breaker a little shorter, for 12 hours earlier, because I realized that the NSA code breaker closes at the December 9th on the 11:55 a.m., not p.m. So please finish the NSA code breaker challenge if you want to get credits out of it. Then please finish that the 11:59 a.m., not p.m. But for the challenges that you submit to the scoring server, you can finish that until the December 9th, 11:95 p.m. Yeah, that's the important thing. Yeah. And then we will have quiz 2 next week. So the quiz 2 will be open on Tuesday, 8:30 a.m. But I will leave it to be opened until the coming Monday, so November 28th, so that you can take the quiz in any time between those 2 dates. Yeah. And then I will use the same policy, 3 attempts, no limit on time. So I will take the highest score, and then you can refer to any class materials during taking the quiz. And then quiz 2 will cover the rest of the part we didn't cover in quiz 1. So including SSL TLS, web security things, and also something related to the code breaker challenge preparation. So we have gone through the analyzing packets, logs, and analyzing a web service. And then I will ask a few questions about that. And then there will be a question for the buffer overflow. So please do not forget to learn more things here in the lecture for today. Any questions for the logistics? So there will be quiz on Tuesday, so there will be no class. So please enjoy your Thanksgiving holiday. Yeah. And then at the same time, you need to take the quiz. Yeah, don't forget about that. So one question from online was will there be a tutorial video again? So for quiz 2, there will be no tutorial video, but the style will be very similar to quiz 1. So while taking the quiz, you have plenty of time to get back to the course material. And then if you follow the slides or videos, then you can easily find the answers. Yeah. So there will be no sample questions, but you don't have to get much of anxiety out of it, because it's an open material policy. And then we have plenty of times. And then I'm expecting someone who already studied everything can finish within 30 minutes. But for those who did not study anything about the quiz, but starting a quiz on that day, then I believe within 3 hours, yeah, you can get the maximum score, I believe. Yeah, in the most of cases. Any other questions for quiz? No, then I will move forward for topics for today. So we will learn about the software vulnerability in general. So we will learn about what are the software errors, and then what are the vulnerabilities, and then what are they? And also, why is that important? Because attackers can exploit that to attack the systems. And we will learn about how that could be possible in a very simple way. And then to learn more details about how the vulnerability exploitation works, we will focus on the very famous vulnerability called the buffer overflow attack. So it has been discovered in 1988. Have you heard about the Morris worm? So that was the first computer virus that spreads over the network. And then one of the students of the Cornell University called, I forgot his first name. Yeah, Robert Morris, maybe, right? Yeah, that guy wrote the malicious program that spreads out over the modem network. And then that actually exploited the buffer overflow vulnerability in the Finger. The program name is called Finger. So it's talking to other users on the system that actually works in our VMCTF1 server. So at that time, that program has a vulnerability and that was exploited. And then after more than 30 years, that is still a problem. Yeah. And then finally, after learning about the vulnerabilities, we will learn about how our security community fight against those vulnerabilities altogether using the CVE database. And then the CVE stands for Common Vulnerabilities Exposures. So the main purpose of that is try to collect the vulnerability information from all across the world and then announce that to public to let others don't use the vulnerable programs and then patch the program and then use the up-to-date program for that. Any questions for the topics before we start for the details? Then let's move forward. So let's think about, before getting into the software industry yet, so let's think about the manufacturing industry. Yeah, so we have had the software industry around 40 to 50 years now, maybe more than that, but not big like this. But 100 years ago, we don't have the term software, and then there's no the personal computer, so that was not developed yet. But even during that time, our manufacturing engineering for manufacturing goods for any kind of thing, for example, building this kind of laptop or just automobiles or something like that. So there are some of the assembly lines, and then human workers. Right now, we use robots to assembly a lot of autos and then something like that. But in the old days, and then still, we have a lot of a manual effort to create some of the goods. So still in some of the manufacturing factory, workers are working like this. So they are sitting on some fixed position, and then the assembly lines providing all the parts that they need to assembly, and then they just do the assembly based on the instructions. But the problem is that the humans are not machines. So for the automobiles or other machines or even computers, yeah, if you let them do some of the work, they can reliably finish. No matter how the big task is, it will take a little more time, but it will finish the work. But the humans are not like that. So generally, humans are prone to errors. So we all make some of the mistake, even if we always recall that oh, don't make the mistake in this quiz or exam. So even if we do that, so we make some mistakes. And then there are many causes for that. So it could be just a simple mistake, or it could be caused by the work was too stressful or worked for too many hours, maybe more than 70, 80 hours per week. Then humans' attention level goes down, and then that actually causes a lot of the errors. And most importantly, the reason why this kind of the manufacturing work requires the intense job, intense workload, stressful workload, is that they do have their production cycle. If they miss the production cycle by 1 day, then there could be a lot of damage on the company's revenue. So if there's a date that one need to submit all the goods to some other company, then the workers are working hard, and then that also creates a lot of chances to make a mistake on their employees. So in this kind of the manufacturing goods, so if that is the automobile industry, if you make a mistake in there, then it could be something like a failure of the car in the road. Then that could be a little benign, but that kind of error in construction industries could be resulting in the collapsing of the entire building. So even if you make a very simple little mistake in it. And then have you heard about the incident in 1983 about like there was a launch of the spaceship, and then that was like they exploded while launching. And the main reason for that is like the different engineers from different countries worked all together. And then some of the European engineers, they are using in SI metric, meter, second, and kilogram, that kind of metrics, while the US engineers working on the pound and feet, that kind of metrics. So that they do have the different specification number on the metric and then like the imperial side. So their specification was not matched. So some of the components are not perfectly fit. And then that small mistake made the entire like the project was like the stopped like that. So the important thing is like the implication that I would like to deliver here is that in the manufacturing industry, we have learned a lot about like the making mistakes in there could result in like the disaster like this. And then same thing happens in the software industry. So developers, human engineers are writing the code. Same thing happens. Humans are prone to errors. And the same thing happens. Many developers, they say that, oh, our company has a work-life balance. Sometimes it's true, but please ask that again if their company has a production due cycle. So like one of the example is that like in 8 years ago, I found a vulnerability in Apple's iPhone device. And then I reported that to Apple. And then Apple wants to make their product do not have any kind of vulnerability before launching of the iOS 8. That was like the new OS at that time. Yeah, that was right. And then that was scheduled to be released in July, but I reported the vulnerability in April. So they do have 3 month cycle for fixing the vulnerability. And then to fix the vulnerability, they need to change the entire operating system and then test it again. And then, so in their regular schedule, they plan to like finish iOS 8 development in July, but there was an incident. I report the vulnerability in April, so they have additional work. And then during the interaction with that company, so they incidentally click the reply to all when they are replying the message to me. So I can see that all the message thread between the company executives and then developers and then mid managers. And then I can see the timelines that like replying on 3 a.m., 4 a.m., 6 a.m. Yeah. And then all these guys are based on the US West Coast time. Yeah. So that means like in some cases, developers are working hard like that. And then in that kind of intense schedule, we can easily guess that there could be some stressful work and then difficult work, and then like sleep depression, and then that actually makes a lot of increase the opportunity of like having a mistake in writing code a lot. Yeah. And then this is the one of the part that the human makes an error, and there's another reason that the software vulnerabilities, so we cannot prevent that from keep happening in the wild. So another reason is that the modern software is very complex. And then how can I put it? The speed of like the increasing in complexity is quite fast. Yeah. And then like I searched for the internet and then try to gather like how many lines of code are in there in Google Chrome, because that is the web browser, the most popular web browser in the world, and many people uses that. And then in 10 years ago from Quora, I can get the answer for like a Google Chrome has around more than 4 million lines of the code without comments. That's quite huge. Then think about like how many lines of code you have written in your lifetime. Yeah. So several millions of lines of the code, that's far much lines than like you have written the code. Yeah. So that means if one component has a vulnerability, developer need to analyze what other components are affected by this vulnerability. So the complexity goes up as the program size goes up. And then generally the complexity increases as a O(n) square, because the specific line that does not cause the vulnerability itself, and then that is related with the other lines of the code. So like the complexity, you can regard the complexity increases like the order of n square or more than that. And then the more interesting statistics is that, so 10 years later for today, so it's actually 8 years later, because this statistics stops at the 2020. And in Google Chrome, we can see that more than 34 million lines of code in there. So it's getting more and more complex. And then you can see that how many lines are added in 2014, 15, 16. And then that's where when the Google Chrome gets super fast in those days. And then to make it more performant and having much more features, developers added many lines. Then that actually resulted in having many vulnerabilities in Google Chrome web browser. And not just for this kind of the web browser, we also use operating system every time. And then in Linux operating system, for example, it used to be having a 12 million lines code in 2015, but now they have more than 27 million, around 30 million lines of code for today. And then same thing happens for Android. We started with around 4 million lines of code, but after around 8 years later, it gets to be 25 million lines of code. So the implications are humans are prone to errors. And then that's the one reason that we will have the vulnerabilities errors in the program. And then work environment, for example, production cycle schedule. So there are ways that we can always applying test and then do the code review. For example, if I write the code and then some of you review the code to reduce the number of mistakes that I made. So that kind of thing is ongoing in most of the companies, but think about the case. If the production cycle gets too close, then they just ignore everything and then just focus on make it work. So that kind of practice makes increases the chance of having the vulnerability in the program. And then lastly, the modern software are too complex. So even if we do all this kind of thing, human labors are not scalable. It scales linearly, but the code complexity scales quadratic. So we cannot catch up that kind of the complexity increasing speed. So we cannot avoid those software vulnerabilities. That's unfortunate. And then we learned about that, that there are causes that having the software errors and vulnerabilities. And then what happens if we made mistake in our software? So it could be resulting in a crash. So I believe when you are coding in Linux or Unix machines and then in C, and I believe that you have seen a lot of this kind of the segmentation fault error, then that happens when you use the memory incorrectly. And if you make that kind of mistake, it will crash like this. And then similar thing happens in the software errors. So whenever you see this kind of some of the software quit unexpectedly, or the operating system shut down unexpectedly. So those kind of things are all caused by the mistake made by developers. So it's something like the case that you are encountered in has not been tested by the Microsoft, Apple, or Linux kernel. And then that could be affected by that could be exploited by the vulnerabilities. And then if just the crash happens, then the result might be something like this. Just crash the program, then we might re-execute the program, and then the problem could be went away. Then it'll be somewhat benign. So it could damage we lost some part of the calculation or something, but we can redo the thing. So in that case, so that kind of errors it's not damaging severely. But the different thing is that for the regular goods, for example, think about your car. To hack your car, I need to be physically close to your car and then get into there. Maybe I can like break your brakes. Then like your car cannot be stopped on like on the highway or something. That could be dangerous. But the precondition of the launching that kind of attack is I need to be close to your vehicle. Right now, it's not holding anymore because modern cars are also connected to the internet. But the dangerous thing about the software vulnerabilities are most of computers and softwares are connected to the internet, and on the internet, anyone can connect to the anywhere, any others. So the hackers in the not close to here, even outside of Oregon, outside the US, maybe from the space, yeah, they can launch the attack. And then for this kind of errors, so if you encounter to this kind of errors, if you are not hackers and then you are not trying to exploit the vulnerability, then it'll just like result in some kind of crash like this. But the different scenario happens if we have a hacker who knows how the vulnerability works, and then who can analyze the thing and who can control over the error to achieve something else that they want to accomplish. So for the hackers, if there is a mistake, then they try to find an error either in source code or applying reverse engineering. So at least they could have the binary program, and then they can analyze that to locate one of the error in the program. And then after they identifying the error, that error would naturally be like the resulting in crash, but they can analyze the crash and try to exploit that error to do something else. And then we call it as writing an exploit. And then writing an exploit means that like the hackers are trying to tame the error to control that to do something else. So if it is not controlled, then it will be resulting in just a segmentation fault, blue screen, and that kind of crash. Just stop it. Restarting it will resolve the problem. But if the hacker controls the error, then they might change the program's behavior to get an administrative access, or they can even delete all files. So as the similar case that we have seen in the manufacturing case, so the software errors could be resulting in this kind of disaster too. So the hackers can steal all your password database and also delete the database. That kind of thing happens. Yeah. And then, as I told you before, yeah, industry knows that this kind of problem a lot. So they have a lot of methods to reduce the mistake from the humans. So first thing is that when we are writing the code for a big program, so we don't write the test case for the entire program, but at least for the part that you wrote, write the thorough test cases to cover. It'll be preferably to have all the cases that could happen, but that could be practically impossible. But in that case, try to write the test cases that could cover the majority of the cases. For example, more than 99.999% or something. Then you will have a very little chance to get an error in that part of code. So the writing test cases are very important. And then the test cases, we cannot generate the complete test cases for all program. And then because of that, another way to do that and to reduce the mistake is let the code to be reviewed by other person. So the taking a code, looking at the different perspective can catch the mistake caused by one person. And then most importantly, because human labors are not scalable, and then code complexity scales the quadratic. So we can also use automatic tools to find this kind of the vulnerabilities. And then we will learn more about those tools in the not coming Monday and next Monday, yeah, after Thanksgiving. So, but the more important thing is even if we know that there are procedures to reduce the mistakes, but that there are many practical reasons that we ignore this kind of practices. And also there is some of the cases that we cannot avoid. So vulnerability happens. Yeah. So any questions about like the background about like this kind of the vulnerabilities, software vulnerabilities? Then I will move forward to introduce one of the notable but simple case of the software vulnerabilities. So in 2014, so there was a bug in the SSL TLS, which is very important for the communication security in the Apple products. So it is written as like the vulnerability hit on like the Apple OS 10, but the OS 10 shares the code with the Apple TV, iPhone, and then watchOS, those kind of the operating systems. So it affects to all the Apple products who share the same code base. And then one of the articles says the anatomy of the go-to-fail vulnerability. Yeah. And then let me explain the details about the vulnerabilities. So whenever like some of the attacks to Apple happens, and then that is archived as like the known one to the community. So Apple tries to fix that in their operating system and their products, and then release the information about like they have fixed that vulnerability. Yeah. And then like right after like one of the hacker figured out there's a vulnerability with using go-to-fail in the Apple's code base, they reported to Apple, and then Apple issued this kind of the announcement that they patched like some of the attacks here. And then this is an example of like the common vulnerability exposures, CVEs. So they do have the CVE numbers, CVE in 2014, and then the number here is like based on the class of the vulnerability, and then like it increases in order. So starting with the 0001, and then increase one by one. Yeah. So it could be the vulnerability like a 1,266 vulnerability in that year. Yeah. So what I just want to tell is like there are so many vulnerabilities in software happening in each year. And then inside there, so the Apple mentions about like the impact is that an attacker with a privileged network position may capture or modify sessions protected by SSL and TLS. So what this line means that attacker with a privileged network position. So the privileged network position means that where you can capture all the packets. So that you might think that having that kind of privilege could be difficult, but I will give you an example that will be very easy a little bit later. And then if the attacker can be on that kind of a network privilege, then what they can do, so although the SSL TLS guarantees that the end-to-end encryption based on the authenticating the certificate, so what attackers can do is like capture and modify the plain text data in the SSL TLS. So we learned that if we use SSL and TLS, then we can ensure that authenticity, confidentiality, and integrity are protected over the communication. So that's what we have learned. But that holds only if the underlying software are intact. And then because of the vulnerability inside of the Apple's SSL TLS module, even if the entire code, the rest of the code are like built safely, because they do have mistake in a single point in the SSL TLS module, they makes like that remove like all the guarantees that the SSL TLS can give. Confidentiality, integrity, these are all gone. And then authenticity is also gone because like they cannot distinguish the messages injected by the attacker or coming from the server side. Yeah. And then the reason was like their module called the secure transport. So this is the module in Apple's operating system that manages the SSL TLS connection, and then they fail to validate the authenticity of the connection. So authenticity is gone, then we can launch the man-in-the-middle attack that we have learned in the class. So that's actually what could happen by exploiting these vulnerabilities. Yeah. Then why do they miss the verification check for the authenticity of the other end? So that mistake is very simple. So this is the part of the code that Apple inserted a mistake in it. And then what it does is it tries to calculate the SHA-1 hash, and then from the buffer, create the hash, make it ready to be like calculating the hash, and then it tries to calculate the hash by updating that with the server random, client random, those kind of the transmitting data over the TLS connection. So we learned that to establish the shared key or something, what we need to do is like we need to hash all the traffic between the client and server. So that's the part that I'm processing in this code. So all these code snippets are okay because like if there's no error, then it will go to SSL raw verify. That's the expected behavior. Yeah. And then if there's no error in SHA-1 hash, then yeah, it's okay. But the problem is happening at here. So this part is also okay. Try to update your hash with some of the signed parameters. And then if there's no error, then it will pass. But the problem is that the developer mistakenly put the go to fail here again. So that we can easily expect that the patterns of the code are very similar. So one of the way to writing this kind of a code is like I wrote like one single line for this one, and then try to copy and paste, and then change the wordings. Yeah, that could be one of the method. And then in doing that, it's quite natural that you might leave one go to fail at the end. But the important thing here is that, so this go to fail is bound to this if condition. So only if this function run resulting in error code that is not 0, then it goes to fail. But the second go to fail, it does not belong to any kind of the if clause. Yeah. So what happens is that after passing this check for the legitimate execution, it will run go to fail and then skipping this verification and then move to the failure, the handling part. Yeah, that's the vulnerability. And then very simple, inserting one more lines of the go to fail, but that could be resulting in like the decrypting all the SSL TLS traffic from the Apple devices. Yeah. So with this, it's skipping the verification step. So have you heard about some of the common practice that whenever you write an if condition in C language, there are two ways you can attach one line immediately after that if condition that will be automatically included in the if clause, even if there's no braces. Yeah. So and then another way is like that you can write the braces and then you can put many lines, and then all of those lines belongs to that if clause. But here, the developer made a bad practice. A good practice is that even if you have a single lines of the code that you want to include in the if clause, always use braces. That's the good practice, and to avoid this kind of the mistake. So if you are not like following that kind of practice, I know that it could be silly. If you know that like there will be only single line, then you want to be more convenient, and then you can be more efficient for reducing the number of keystrokes. But I do not recommend doing that. So please always use braces to the if clauses to make sure that which lines are included and which lines are not included. So after thoroughly analyzing the code, you can immediately find that this is a vulnerability. But if this code, snippet of code, is hidden in the several millions of lines of the code, then the developers might miss like this kind of error. Yeah. And then let's learn a little more about what attackers can do out of this vulnerability. So I previously told that like the attacker need to have the privilege that they can monitor the network. And then how can you make this as a realistic attack scenario is that, so suppose I'm an attacker, then if I want to exploit that vulnerability, what I would like to do first is go to Starbucks at the downtown, and then open my hotspot, and then name it as like a Google free Starbucks Wi-Fi. Yeah. Then Starbucks patrons, they will see two different Wi-Fi, but they might connect to my Wi-Fi, and then they don't care about like the authenticity, legitimacy. If I show the similar UI or something like that, they will just trust it and then accept and continue, and then use the Wi-Fi. And then we can also create this as a wireless free Wi-Fi that many people connected it. Then we can naturally have the network privilege in there, because I installed that router, Wi-Fi router, and then I can configure that Wi-Fi router as like the commanded by myself. And then after that, so suppose one of the victim got connected to my Wi-Fi router, and then whenever I observe that that is Apple device, and then that tries to make an SSL connection, then what I can do is like I can trigger that go to fail, try to make the client not verifying the certificate, and then I work as a man in the middle between the Google server and the client, and then steal all the plain text password. And also we can insert malicious data to be delivered to the client side. Yeah. So as a result, they can pretend as a google.com, facebook.com, and they can steal all the cookies, password. Yeah, that could happen. So that was very serious vulnerability. And then, so another thing that they can do is like some of the browsers are using fixed certificate, and then that tries to avoid like any kind of the man in the middle attack. And then in that case, what attackers can do is they can alter the client network packet, and then they will not verify the hash of the entire network traffic because of the go to fail error. Yeah. And then what we can do is like because the server will decide which cipher suit we will use. So recall the TLS protocol. Client sends a set of the cipher suit, and then server will choose one of that. And then what we will do as a network router is that we alter the server packet to indicate that they chose cryptographic protocol, which is known to be weak. So what we will do is like if we will tell a lie about like a client included that cipher suit, and then server tries to use that cipher suit. Yeah. And in that case, they will communicate with the weak cipher suit, and then in the middle, we can actually launch the attack to break that cryptography. So that's actually possible because RC5, that algorithm is included in the SSL and TLS standard. And then we can force to the client and server use this algorithm. And then this algorithm is known to be broken in 2 to the 44 execution, which is a big number, but not that huge number in comparison to like in the era of like a Bitcoin mining kind of thing. Yeah, so that kind of attack is possible. So go to fail example was a very simple mistake. So natural way, developers try to copy and paste and edit the code, and then that could happen. And then it just added one line of the code, but the mistake, even if the mistake was simple, the impact is huge. Yeah. So attackers can hijack the TLS protected connection, and then that's what we are relying on every day, because in checking the email or other like the connecting to Canvas, we all use the HTTPS that's based on TLS, and then that could be attacked by like this vulnerability. Yeah. So the implications are, so for the software vulnerabilities, even if that is a very simple one, because the attackers can take control over that, so that could be result in like the disaster. And then that kind of disaster is not arbitrarily happening. So if it is arbitrarily runs an error, then it will be causing just a crash, or like cannot make the connection over TLS. But because hackers, they also have brain, and then try to analyze the code and then try to control the vulnerability, then they can achieve what they want to do. So those errors could be controlled by attackers. And then that'll be much easier if those machines are connected over the internet, because attackers can launch the attack remotely. Yeah. So any questions about the Apple's go-to-fail vulnerability and then like the exploitation example of that vulnerability? Right, then I will move on to the next. So for next, I would like to introduce one class of the vulnerability, and then the most popular vulnerability class called the buffer overflow vulnerability. So conceptually, the vulnerability itself is very simple. So vulnerability is a bug that happens if the program puts more data than a buffer can contain. So for example, suppose you have a character buffer size 16. So it's just a 16 bytes. But you may write a code to copy the string, which is definitely longer than 16 bytes, to the buffer. So modern compilers, if you run this kind of code, it may generate the error that like the string copy is insecure. Don't use that. You need to check the size of the target string, the source string, before copying the string to the buffer, because that could be longer than that. So the modern compilers are giving warnings to that, but it's not a definite error. So I know that many students ignores compilation warnings because they are not stopping you to run the program. So if you are with the short time window for the homework due date, then you might ignore all the warnings and then proceed for that. So that is a bad practice. So if you have a compilation errors or a perpetration warnings, please regard that as that could be turned into like a security vulnerability, and then try to analyze that, whether that could be exploited or not. And then one of the practice that I also make is like in my make file for the build script, I usually enable like the option called the -w all. So that will generate the warnings for all the possible warnings of the compiler, and then adding another flag called the -w error. So my compiler option regards all the warnings as error. So that means like if there's a warnings, I need to fix my code to make it a binary program and run it. So that kind of process, yeah, definitely it increased the development time, but that actually reduced the mistakes that you can make. Yeah. And then that's the basic of the buffer overflow vulnerabilities. And then if it is not controlled, then it will just crash. Yeah. And then the reason why this kind of the buffer overflow is problematic is it does not just tainting the data outside the buffer. And this kind of the local variable, these are usually stored into so-called program stack. And then the computer systems, when they are calling a function and then return to the upper level function. So think about it, all the C programs starting with the main function, but you will call a lot of function out of it. But the program knows that where to return after finishing the function execution. Then that kind of information are all written in the program stack, and the buffer overflow attack can change data in the program stack to make the return address to be the totally different address. So the programs need to run as expected, but with the buffer overflow vulnerability, and that can be resulted in running a totally different part of the code. Yeah. So what that means is that like even if there's a no code snippet that removing all the files in the system or something, what attackers can do is they can take control of buffer overflow vulnerability to run this kind of a code. So if there's a delete all function in the program, they can invoke it and then delete everything. Otherwise, so in the C library, if we write the code in C and then like load into the system, then the C library will be automatically loaded. And then they do have function called the system. And then that actually runs command as an argument. And then if we can invoke this kind of function, then if we insert remove recursively forced from the root. Then that will remove entire thing from the computer system. So this kind of thing can happen. And before getting into the details about the buffer overflow vulnerability, we all need to understand how this program stack works. And then I will not getting into too detail about that, but I want to be at a very high level. But I have to show some of the assembly lines to you so that don't get haunted by that. So the program stack is something look like this. And then it is automatically managed by the compilers when they are generating program. And then let's take an example of this snippet of the code. So suppose we have a function called func, and then it will take two arguments from the outside, myArg1 and myArg2. And then internally, it may use the local variable a, b, c as an integer. And then it might call func2 using the a and b local variables as its arguments. Then how the compilers and programs are using the program stack is, so in the Intel CPU, we have many registers, and then we reserve two registers for defining a program stack. And one is called the EBP. So E means the extended, because Intel processors are developed in 8 bits, extended to 16 bits, extended to 32 bits, and then extended to 64 bits. So this E something register is attached to the 32-bit computers. So EBP means the extended base pointer. So it points to the base of the stack. So it points to the bottom of the stack. And then ESP, extended stack pointer, it points to the top of the stack. And then the important thing here is that we all learn the stack as growing upwards, right? But in this kind of program stack, it grows actually the downwards. So you need to think it upside down. So this is actually the stack top. So if we push on the stack, we will add one more element here. And then if we pop the stack, then ESP will go down to pop one block of the data out of it. And then in the 32-bit computer, you can regard all this data width is 4 bytes. And then if it is a 64-bit computer, then that could be 8 bytes. But we are working on the examples of the 32-bit one because that's more simple. So you can regard that each block is like the 4 byte of the data. Yeah. So this is stack top and this is stack bottom. And then base pointer and then stack pointer defines where the stack ends and starts. Yeah. And then let's get back to this code example. So whenever we invoke this function, compiler will generate the code for us. The CPU can manage program stack like this. So once we get into like the execution for function 2 here, yeah, then our program stack would look like this. And then one of the important invariant characteristics about this kind of program stack is, so for a function, we could get like some arguments from the caller. Yeah. So the caller prepares the arguments here and then call my function. So that we can find the argument coming from caller from the above the address of the EBP. So for the variable, for the variables, so we store the argument variable that comes from the caller at the bottom of the stack. So we need to make the positive index over EBP. And then for the local variables, we store them within the base pointer and then stack pointer. Yeah. So that's the program stack allocated by like this function. So we store local variable A, B, and C in the middle of like a stack start and end. And then whenever we make another function call, as a caller, we need to deliver the arguments to the callee function. And to do that, we put that at the bottom of the stack and then call the function. Then if we make the function 2 function call, then these two will be the argument, and then there will be return address, save the base pointer, and then their local stack starts. Yeah. So this is generally how the program stack works. So I can understand that some of you are not clear about how it works, but I will take the questions some later moment after you see that how the buffer overflow attack works, because like seeing that would helpful for understanding how the program works entirely. So let's get into the challenge binary program. So I created one challenge that has 2 flags inside of it. And then the program name is BOF, buffer overflow. And then what it does is like the inside of the program, you have the function called the process user input. And then what it does is, so it has a flag variable and the buffer. And then we set the flag as this fake flag. But if you submit the fake flag to our scoring system, because it's fake, it does not give the credit. But your objective is like you need to read this flag 1. Yeah. So in the regular execution of the program, because we set the flag as a fake flag, and then we print the address of the flag 1, address of the fake flag, and then address of the one of the function, and then address of the current flag variable. So it just print out the values for your information. So you can actually ignore these parts because it does not affect the program's execution. And then after that, it will ask you to provide some of the input, and then it will get your input from the standard in, from the console input, and then put that into the buffer up to 128 characters. So can you see the buffer overflow vulnerability here? So we have a buffer size as 12, but we can put up to 128 characters. So buffer is a 12 size, but we can fill more than that. Yeah. And then, so the vulnerability is here. The buffer size is 12, but we can fill up to 128 bytes. Then my question is that can you overflow this buffer to overwrite this flag variable? So right now it is pointing to the fake flag, but can you make it to point to flag 1 and read that from here? Yeah. So that's possible. Yeah. And then let's get into the details of like how we can control that and to achieve and then read the flag out of it. Yeah, question?
So on the CTF website, is there a link to download the VOF.c file?
So you can get into the VMCTF1 server and then fetch software, then you will see the binary program. The binary program is hosted in the VMCTF1 server. And then I will make sure to add that description in the challenge description. Yeah. Sorry about that. I wrote that description like 2 minutes before I came to the class. So, I emphasize that if there's a production due cycle is close, then there is a mistake. Yeah. So this is the example screen of the execution of the program. So it prints out some of the addresses for your information. So your flag address, the flag 1, is at this address, 760. But your current flag variable stores the fake flag address, which is like a 77C. So in the print of like a flag variable, you will see that this address is available for the fake flag. And then if I give like a 0 byte to the input, I did not overflow any kind of buffer, so it will execute as is. So they will use this flag address, so it will print out the fake flag. So we need to make the program to change their behavior to print out the flag 1 here, not the fake flag here. So we need to change the address stored something 77C stored into the flag variable to the something 760 to change the address. And then let's take a look at how we can do that. And then I removed all the unnecessary printf because that's required for like getting the address. Yeah. So to simplify the code execution, I simply removed those lines of the code and then simplify the code. And then if we get into the execution of this function, our program stack would look like this. So we are making the fgets with the buffer 128 and standout in. So as a caller, if we make the function call, we need to prepare those kind of arguments at here. Yeah. And then for the local variables, so we have a buffer 12 bytes. So buffer is at here. And then because each box, you can regard that as a 4 bytes because it's a 32-bit computer. So we have a 3 blocks as a 12 bytes. And then buffer from 0 to 3 can be here, 4 to 7 can be here, and then 8 to 11. So the last one is a not inclusive index. So that those kind of the 12 bytes could be stored in here. And then how the compiler generates, allocates the local variable in the stack is just contiguous and adjacent. So right after that, we have a flag variable. So the compilers puts the flag variable here, and then from the code, we put the fake flag in the flag variable. So that's the current status. So when we make a function call to fgets, then this is actually the assembly line to put the std in the stack, and then put the size of 120 in the stack, and then put the buffer. So buffer is at the EBP minus 0x18. So like this number is actually matches to where the buffer is. Yeah. And then if you are making a printf function call that has 2 arguments, then how it works is like it will push the minus C EBP. So actually the pushing the last one. And then we can also see that the EBP minus C is the location of the flag variable. And then put this kind of string and then call printf. That's how it works for making a function call. Yeah. So now you know that the program stack for the buffer overflow target program would be like this when we get into the target function execution. And then here, what we will do is, so previously I just press enter, but instead of doing that, I try to type 11 characters of A and then press enter. Yeah. The reason why I put the 11 character, not the 12 characters, is that the fgets function. So fget string, and then the definition of the string in C language is that it should always have the 0 character at the end. So if I type 11 character of A, then fgets will automatically add 0 byte at the end. So entirely, that could be 12 bytes. Yeah. So what I did is like that I typed the 11 A's and type enter. And then my input is 11 character and then 0 character that is not printed. So that I just put the 12 characters. Then how it works is something like this. So take a look at this. So we are filling the buffer from here, and then we put 11 characters of A, and then at the end, we put 0 for that. So we fill the 12 bytes of the buffer. And then because our buffer size is 12, there's no buffer overflow happen. Yeah. This is the benign case. But let's take a look at what if we put the 12 bytes of A and then press enter. Then it will actually write the 13 bytes to the buffer. And then how it works is, so we put the 12 bytes of A in the buffer, and then the tailing, the 0 bytes need to be written in the 13th bytes. And then that's actually the last byte of the flag variable. Yeah. So we are seeing that the last address of the flag variable has been changed as a 0. Yeah. And then as a result, it does not refer to the fake flag address. Instead of that, it refers to the 700 and then printing some of the data inside of there. So I also don't know what kind of data is there, but at least we have seen that we can change the program's behavior by changing the flag address. Yeah. So the implication here is that, so if we allocate the local variables in the function, they are adjacent each other, and then compilers are just putting that adjacent in the program stack. So if we can overflow one of the variable, then that could change the value of the other variables. That's the basic of the buffer overflow attack. Then let's move forward for like the having more control out of it. So we just put 0, but let's change this address to flag address. We can actually do that. So if I type 12 A's and then enter, then it puts 0 on it. But if we put the more characters on there, then we can change the flag value as we wish. So for example, the address of the flag, the real flag, not the fake flag, is like the 0A048760 as a hexadecimal. And then because the Intel processors are using little endian, so what that means is that like if there's an integer number like this, then the Intel processors, so this is a 4-byte integer, and then for the first byte, they takes the last 2 digit and then put it on here. And then second last 2 digit as a second byte, third byte, and then first byte. So the order is like least significant bit to the most significant bit. And then this is called little endian because we put the least significant bit first. Yeah. And then that's how interprocessors are working. So if we want to put, for example, if we want to put an integer value 41424344, then we need to put the byte data in backwards. 44434241. Then that's why I put the address in backward. So if I want to put this address, and then in bytes order, we need to inverse it in each byte. So I put 60 first, 87 second, 04 as a third, and then 08 as the last. Yeah. And then what I will do is, so because we cannot type this kind of the characters, I will use a program to generate that kind of values as a string. So in C language, anything that does not a null character, it does not cut the string. So any character other than null could be a character in the string. So this is totally possible. So what I will do is putting 12 of A's to fill this buffer. And then right after that, I put 60870408. Then all these bytes are interpreted in backward to conform an integer value. Then that's actually the address of the flag. And then if we change the address of flag like that, then the program says your flag address is 760, which is the flag, not the fake flag. Then as a result, the last printf function was print your flag is printing the flag. And then how that works is like it will just flag, it will just print out where the flag is, then it will print out the real flag, not the hidden one. But I run this with the scrambled application. So that's why it says like the flag is hidden. But if you launch the attack in the real challenge program, then you will get the flag out of it. Yeah. So that's the first attack that you can launch. Yeah. Any questions about this attack? Yes.
Can you explain again like how you like in the top like get your address?
Pardon?
Like how do you like on the top line, right? Like
so for these kind of addresses, so 60 is actually the character, but the 87, 04, 08, these are not printable character, so that you cannot type it. So to put those values, you need to use a program to build a string.
We need to make that other program by ourselves.
Yes. And then like the Python, so we can write a Python script, but with the -c option, we can actually run this kind of the code snippet as an inline code in Python. So what it will do is like it will interpret this argument, print something as a Python code, and then it will print out this kind of data to the console. And then because we have a pipe on it, so that output will be delivered as an input to the buffer overflow program. So by using pipe, instead of like we are delivering our keystroke to the program, we can deliver the output of the another program to the another program. Yeah, that's how it works. Yeah. And then let's move on to the next. Yeah. So please ignore this blue arrow right now, so that will be used in later. So that now we know that using the exploiting the buffer overflow vulnerability, we can change the variable content, which is adjacent to the buffer. Yeah, but the buffer overflow is much more powerful than just changing the variable. And then it actually can control the program's behaviors arbitrarily, not just changing the flag variable. It can actually run any kind of thing. And then let me describe about like how that works. So how this program works is that like at the entry, it has a main function. And then main function invokes this process user input function. Yeah. And then in doing that, main function runs this function. And then after that, this function runs. So it'll be starting from here to there. Then it will be finishing their execution. And then after finishing the execution, if this function returns, it should return right after the function call, right? That's the expected behavior. Yeah. So if the main function calls this function, it runs, and then after finishing this function, it must return to the end of the next line of the main function. And then because there's no line, the main function returns, and then program is over. That's how it works. Yeah. So main function continues like this. Yeah. Then one question is that how the program knows that after finishing this function, it must return to the end of the main function. So this is actually not fixed by this function. So that this function can be called by the main function, or there could be function 1, 2, 3, and then inside those functions, they can call this process user input. So in that case, our function need to return the colors place, right? So we cannot determine like that this function should return to the single point. There could be many places that this function should return. And at the runtime, we actually keeping record of like where the function should return whenever the function is invoked. Because at the color, it's very easy to locate where it should return. So for example, whenever you call a function, that function should return right next line of that function call. That's simple. And then compilers are actually storing that kind of information in the program stack called as a return address. Yeah. So how it works is that, so starting from the main function, if the main function invokes the process user input, then they will invoke it. And then right before running that code, what it will do is it will put the next line of the main function address as a return address. So that is stored at here. And then this function runs. And then when this function returns, then it will refer to their own program stack for the return address part. And then we previously stored this position right after the calling that function as a return address. So they know that they should return to here. That's how program manages call and return pair matching. And then, so you can think it up like if there's a main function that calls function 1, that calls function 2, that calls function 3, nested like that, then we will have this kind of program stack nested. And then whenever it returns, go up and up, and then it will refer to the return address of their own program stack. And then that's how we can build a stack backtrace and those kind of things. And then from the buffer, we can overflow from here to overwrite flag. But that means if we put more data, then we can also overwrite this return address. Then we can fool the program that after running this function, not returning to here, then we can make them to returning to somewhere else, arbitrary address that we put. So let's take a look at how it works. So suppose we put the 12 A's. What happens is like that we just fill the buffer. And then if we put the address of the flag 1, then that will overwrite the flag variable. Then after that, what we can do is like, let's overwrite 12 more A's. And then another thing is like we will put 1, 2, 3, 4, 5, 6, 7, 8 at the return address. So the 12 more A's, A. It will skip these 3 blocks, and then putting this address will change the return address. So starting from the buffer, what we can overwrite is like the 128 bytes, but the amount of the data we need is like 32 bytes, right? So that's much smaller than the buffer that we can, like the input that we can give. Then we can definitely overwrite the return address. And then if we put like a 1, 2, 3, 4, 5, 6, 7, 8, that's not a valid address, so the program will crash. But if you point the correct address of the program at here, then that will run. So to make the attack easier, so inside of the buffer overflow program, I put the shell function. And then in the program, I do not invoke this function at all. Yeah. And then what it does is like it tries to inherit the privilege of the program and then run a bash. So the bash is command line shell. After running the bash, you can run any kind of program that you wish. And then because of this line, your shell will inherit the privilege that the binary program has. So you have already seen that for the most of the challenges on the server, you cannot read the flag directly, but you can read the flag using the program that I prepared. The reason is like while executing the program, it has a privilege to read the flag. But if you just directly try to read the flag, because you don't have the privilege, you cannot read that. But here, our buffer overflow program is running in a higher privilege. Then while executing this program, if we change the return address and then run this function, then we can inherit this privilege and then run bash shell. Then from here, we can freely read about the flag. So that's how the attack runs. So after running bin bash, so you can run cat flag to read the flag. And then for next, let me describe how the entire attack works. So from the address output, we previously used the flag address and then put that address in a flag variable. But in this case, we are doing that. And on top of that, we will also change the return address. And then the program, thankfully, let us know about where the shell address is. So that's actually 804858B. Yeah. And then let's take a look at how we can overflow the buffer. So the input that I will give is like the 12 A's to fill about the buffer, and then 4 bytes of the flag address to make the flag variable points to the real flag, not the fake flag. And then put 12 bytes of the A to fill these 2 white blocks and then save the EBP, and then put this address, the address for shell function at the end to overwrite the return address. So how it works is like, if this kind of the input delivered to the buffer overflow binary program, then it will put 12 A's, flag address, and then put 12 more A's up to this point, and then put this address. And then you will see that like I put the address in a inverse order because inter CPU follows the little endian 8B850408. Then the return address will be changing like this. So after delivering that input, we have this kind of the program stack. And then let's see what will happen. So when so in the normal case, when this function returns, it refers to the stored return address, which was right after the function call in the main function. That was the normal execution. But with the attack, your program stack will be changed like this. And then at the end of a function execution, it will refer to this return address. And then the address is totally different than like the end of the main function. So that's actually the start of the shell function. So it will return to the start of the shell function. That's how you can change the control flow of the program. So the program will never invoke shell function. But by exploiting the buffer overflow vulnerability happening here, you can return that function into the totally different function. And then this kind of the attack is so-called like the arbitrary code execution, because you can execute any kind of code if you name any kind of address. Yeah. So by exploiting the buffer overflow vulnerability, we can launch the arbitrary code execution attack. So the result is something like this. So the reason why we cannot read the flag is, so without exploitation, my account does not have the group ID for the challenge. So it has a group ID of like my own ID, but the flag file, so there's no permission for any users, but the read permission for the user and groups. So the user root or group for this solved, yeah, they can read the thing. So because I don't have that kind of group ID, I cannot read that. But after you finish this kind of exploitation, and then the shell function runs, it will inherit the privilege and then run the shell. So if you run the same command ID after the exploitation, you will have the inherited group ID. So because this group matches with this one, so you can read the flag. So any questions for the program stack and the buffer overflow vulnerability? Yes.
So is there a possibility that like you could create a malicious program and then you could like, let's say that we're like remotely connected to a server or something and we find that we can like execute a buffer overflow attack. Can you point the address to like your local machine's address of the start point of the malicious program, or does it have to be on the server?
So that has to be on the server. So what you can think of is like so basically what we can do is we can change the return address, and then that actually allows reusing the existing code in the server.
Yeah.
And then you might be curious about, so this is a challenge, and then I wrote the program, and then to make it easy, so I put this kind of shell function, but you might have a conjecture that like who like an idiot developer put that kind of function in their program, right?
Yeah.
So that there will be no code like this. Yeah, but there is an attack, then we can avoid that. So not in these days, right now we are separating data and code, and then we can run on the data. But before 2014, it's quite recent. Yeah, it's 8 years ago, but recent, because buffer overflow was discovered in more than 30 years ago.
Yeah.
So before 2014, so we can execute on the data. So what we can do is, so suppose you can overwrite the buffer and then overwrite the return address. And then after the return address, you can actually compile this function and then generate the binary opcode of that function, and then put those kind of the code in the buffer, and then put the return address as the code address. Then what you can do is like you are actually injecting the code to the server, then that buffer will be stored into the server, and then changing the return address to that point. So even if you don't have this kind of code, you can write the code and then put that on the server and run it.
Okay,
so that is still called the shell code, because the most popular objective of the attackers is getting a shell. After getting a shell, they can do whatever they want. That's why, and then that's why we call that as a shell code. So if we write a shell code, then like we can put that on the server and then exploit that. And then I actually teach more details of this kind of thing for 10 weeks in a different class, so-called the cyber attack and defense. So if you're interested in like learning more about this kind of technical stuff, please get into that class. I know that right now it is capped with the 25 students for the undergrad, so it is fully filled, but I will ask the school to increase that to 50 or 60, so to accommodate like all the students who are interested in that kind of thing. Yeah. Yes.
How do you know how to price apart the safe knowledge and the flag, like
so it's not always like that. So the program stack for this specific program looks like this. And then you are curious about like how can you identify where it is? So to do that, we actually need to read the assembly of the program. And then, so take a look at this assembly code. So that once it is compiled, assembly code will never change it. And then from this app-gets function, and then this is the corresponding app-gets in the assembly. Then for the first argument is the buffer. And then we are curious about where the buffer is, right? And then first argument of the buffer comes from the EBP minus 0x18. That's where we can find the location of the buffer relative to the EBP. And then another important thing is that the return address is always stored in the +4 of EBP. That's fixed. So what we need to do is like, because this is fixed, so the problem that we need to solve is like we need to locate where the buffer is. And then for doing that, we can read the assembly, and then we can easily find that. Yeah. That's the thing. Any other questions for the buffer overflow attacks? So I know that I oversimplified the entire attack. So like that's why I recommend like taking the cyber attack and defense class, because like after like that 10 weeks of the course, like you will be much clearer about like this kind of attack. Yeah, but I cannot teach those kind of the 10 weeks thing in one class, so that's why I simplified it. Yeah. And then let's move on to next. So I just introduced the one class of the vulnerability, buffer overflow. Yeah, and then there are many other classes of the vulnerabilities, but to point more notable things, so more frequent and then dangerous vulnerabilities are, so that there is a vulnerability called the format string vulnerability. And then the format strings are something like you use for printf, %d, %p, those kind of the %s, that kind of thing. And then, so for the most of the cases, we use printf using this kind of the fixed string as a format string. But in writing the programs, there could be a case that you want to programmatically generate those kind of format string. And then in that case, we can put the format string as a buffer and then call the printf like this. And then the vulnerability happens if that kind of buffer is controllable by the attacker. So suppose we want to call a printf function with the buffer 1 and 2 and 3. Yeah. And then if your input comes like %d, %x, %p, then it will regard first argument as 1, second argument as 2, third argument as 3. So it will print out like this. But what happened if I put more %d, %p, those kind of things in the input? So the interesting thing is that for the printf function, there is no limit in the argument length. So we don't know how many arguments were passed. So I will use this kind of a program stack. So when we call a printf function, we will put the buffer at here, and then 1, 2, 3 are there. So if we use first %p, then it will print this one. Second %p, third %p, and then if we do it again and again, then it will print out the return address. So how we can use a format string attack is, so in this kind of case, if we put a lot of %p or %d, actually we can read the program stack and get out of the console input and then interpret that kind of integer variable to do the recon about like the system. So that we can actually get what's the return address, what's the flag address, and then those kind of information. And then another thing is like the printf has an interesting directive called %n. Have you ever used that directive in printf? I believe not so, because I also never used that, not in the regular program, but I have used it a lot in the attacking the others. And then what %n does is, so %n takes an address, and then it will put the number of characters printed by current printf call to that variable. Yeah. So it's something like, if we %n, and then that %n goes to the specific address, then we can actually write value on it. So for example, so using printf, you can actually change the return address. How can you do that is, so %p, p, 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 again and again, then eventually it will reach to the return address. Yeah. But in the one of the buffer, suppose you can put the address of the return address. And then at this position, you run the %n with the printf. Then suppose you have printed this number of characters to the console with the printf and run printen, then that will overwrite the return address like this address. So I can feel that many got lost about like what my description. So the important thing here is that, so printf function call their format string, because like the printf function call does not have a limit on the argument number, and then they don't know how many arguments are passed by. And then it has the functionality that we can overwrite some of the value and then read some of the value. So if it is exploited well, then the attacker can have the capability that they can overwrite any kind of memory address, and then they can read any kind of memory address. So what they can do is, using that capability, so it is so-called arbitrary read capability and arbitrary write capability. So have you guys learned about the Turing machine? So the Turing machine is a conceptual machine of the computer. And then what Turing machine does is like, there's a memory, and then we just move on the memory, write it, read it, that's it. So think about arbitrary read and write. From the memory, we can read any value. We can write any value. So theoretically, using printf format string attack, we can build a Turing machine out of it. That means that we can do any kind of computation. So that means attacker can run their own separate program in the vulnerable program to do something. And then if that is the case, that'll be okay. But what attacker's program would do is they change the return address to invoke the shell, so that can be possible. So that's how like the format string vulnerability works. And then if you want to get more details of that, in week 6 of the cyber attack and defense, I teach like the format string attacks, and then I have like a good 12 examples of like the exploiting the format string attacks. So if you want to be hardcore and then learn about that, please take the class. And in addition to format string vulnerability, there's another popular vulnerability called the use after free. And then this is all about the malloc and free, that kind of the dynamic memory management. And then the case of the happening, the use after free is quite simple. So suppose you have 4 different functions, function 1, 2, and 3, and 4. And then we call those functions in the main function. And then what function 1 does, it will allocate the 16 byte of the memory and then copy the hello world string in here and then return that. So this pointer m will store the pointer for the hello world. And then we will move that pointer to function 2. And what it does is it's free the memory because we will not use that one. And then after that, we call function 3, and it will allocate the memory again as a different variable and then put the not hello world, different string in there. And then function 4, later, it just print out the pointer m, not the m2 allocated here. But so that must be error because we allocate the memory m here in function 1, but we freed it in function 2. But how the system's memory management mechanism works is that, so they have a pool of the malloc allocatable memory blocks. And then whenever there's a request, they just get 16 byte block and then give it to the program. And then once it is being freed, then they will cache this location as a freed list. And then next time the same size allocation comes in, they just give it, not refer to the same memory. So what's happening internal is that, so even if the memory here is being freed, because the size of the allocation is the same, so the address of the M2 will be the same as the address of M, even if they are in this different variable. And then in the program's semantic, because we freed memory M in function 2, function 4 should never use M because that's invalid address. But because we don't clear up the address value, so that points to the sum of the heap address. And then if the function 3 allocates another memory at here, then we can read that kind of the different object data. And then this is actually the allocate free, and then using the pointer after free. So that's called the use after free. So it's something like at the construction, we point to one of the data. And then later it could be freed. But when we are freeing the memory, we are not resetting the pointer itself. Pointer points there, but there's nothing. But then later, while doing some other execution, there is a case that some other allocation happens, then one of the memory block will be allocated here. Then if we use that pointer, then now that address is valid. But that points to the totally different object. Yeah. That's what's happening in like the web browsers a lot. So if you're searching for the vulnerabilities in Google Chrome or something, then you will see a lot of the use after free vulnerabilities. And then that happens a lot with the JavaScript object. So that's why it's so popular in there. Then let's wrap up about like what we learned today, and then like learn more about the implications. So by taking a look at those examples, go to fail, and also buffer overflow vulnerability, and then there are format string vulnerability and use after free vulnerability. So we know that there are so many vulnerabilities and they are critical. But the important thing is like we cannot avoid like if vulnerabilities are like happening in the software program. So if there's a way to build a program that always tell that this program has a vulnerability or not, then problem solved. But the interesting thing is that the great guy, Alan Turing, so he developed the Turing machine. And then after that, he set the bound that some of the problems that Turing machine cannot solve. So it is proven to be like some of the problems that even with the modern computers, even with the the quantum computers, anything, no matter what you do, you cannot solve some of the problems. And then one of the problem is so-called halting problem. And what that is that, so there could be no algorithm that can tell a program stops or not. Yeah. So you can think it as like oh, I can easily tell the program stops. There's a no while loop, it will stop. Yeah, that's the case. But this is for like the general case. Is there an algorithm that can tell for any kind of program? You give that as an input. Can you tell that stops or not? So for that kind of general cases, so it's theoretically impossible to solve that. But in this kind of theory, we have a reduction technique. And then if we define any kind of the semantic of the program, for example, if this program does malicious activity or not, if this program has a vulnerability or not. So for all those kind of problem, we can reduce that as a halting problem. So we can design a program that if there's a vulnerability, halts. If there's no vulnerability, not halts. And then give that as a halting problem input, then we cannot solve it. So theoretically, we cannot build a general algorithm to tell like that there is a vulnerability or not. So in that case, what we can do as a best effort is what we can do is like we can try to create the patterns of the vulnerability. So for example, buffer overflow vulnerability is a one class of the vulnerability, and its pattern is writing more data than the buffer can hold. And then format string vulnerability. So if we programmatically generate the format strings and then let those kind of the thing tainted by the user input or network input, so that could be dangerous. So use of the network or user data in the printf string, yeah, that could be patternized as a defeating the format string attack. Yeah. Then another thing is like as I told you, the software vulnerabilities are like discovered the hundreds of the software vulnerabilities are discovered in each day, and then like human labors are not scalable for that. So another way is like after defining those kind of the vulnerability patterns, we can write an automated algorithm for searching for those specific patterns, not about the telling that program is vulnerable or not. So telling that this pattern exists in the program or not. So it's just a syntax matching, so we can do that. And then another thing is like we can run the program and then give the random input on it and then run it until it crash. And then if we observe the crash, that could be a bug. So that there's a dynamic way to find the vulnerabilities like that. And then we will learn about that in next lecture. And these are about the theoretical limit. And then because there are so many vulnerabilities, there might be need of the community effort to battling against those vulnerabilities and attacks. And then in currently, there is a website and then like this service, so-called CVE, Common Vulnerabilities and Exposures. And because the impact of the vulnerability, once it is hit by some company, their impact and damage could be humongous. So that's why the community built this kind of the service and then try to announce and archive and announce the known vulnerabilities. So how it works? So it is maintained. It is firstly started by the MITRE, so one of the defense contractor, and then the company works with the national lab. So and then later now it's working with the NIST, the standardization like a institution in the United States to collect all the vulnerability information and then announce about that. And then how it works is something like this. So suppose you are a developer of the Nginx server application. And then suppose you found the vulnerability while refactoring the code, you found the buffer overflow vulnerability from the Nginx version here to there. And then after you fix that, and at the same time, you can report there is a exploitable vulnerability in Nginx to NIST or MITRE. And then what they will do is they will issue a CVE number like this, and then archive that as a known vulnerability so that everybody in the world can access that information. And then it includes the description that the, can you read those characters? Buffer overflow in some of the function, some of the C code file and some of the module from version this and that, and then another version this and that, they do have a buffer overflow vulnerability, and then these versions are affected. So that this kind of the information is released in public, and then as a system operators, if you receive that kind of information, then what you need to do is like check if any of the servers, computers running effective version of the program, and if it is, update that. Yeah, that's how we can use CVE. And then this is like the one case, and then there are another cases our CVEs are reported. So the previous cases was like developers are reporting that directly to the like NIST and the MIRE, or there are several white hat hackers. So that they are hackers and then they are hacking for goods. So what they can do is like they analyze the softwares for fun and then try to find the vulnerabilities. And if they find the vulnerability, try to exploit that and exploit that to their own machine, not about like the public server machine, to not damage any others. And then after proving that this vulnerability is severe and critical, do not let others know about that and just reporting that to the vendor. So for example, in 2014, I hacked an Apple iPhone, and then like I reported 7 vulnerabilities to Apple, and then one of the vulnerability was acknowledged as like the common vulnerability exposure. So like the Apple announced like this kind of information in their website, and also like they reported that to the national CVE database, so that this kind of information is released that. And then as the system operators, they can, so for example, if you are managing like some of the defense institution or something, then if one of your employee uses like the iPhone, so this is the content of the iOS 8, but the versions before iOS 8 are vulnerable to this kind of the vulnerability. So if one of the employee uses iOS 7.1 or something, so what you can do as a system operator is like let them update their machines, because like they can hit by like this kind of the vulnerability attacks. And then lastly, I want to introduce like another community effort on like the making the software secure. So have you heard about the Patch Tuesday? So this is a painful term in the cybersecurity, because there are so many software vulnerabilities are reported each day. And then suppose if we update the software every time we receive the report, then we need to have the developers who handle those kind of the errors every day. And then also we will release the patch every day we receive the vulnerability. So that's quite inefficient, because if we, that means like whenever we update the operating system, then all the system operators in the world, they need to update the software again and again. So for the super critical vulnerabilities, they do make the hot fix and then release the patches without this kind of schedule. But for the general vulnerabilities that could be hard to find and hard to exploit, so what they do is they do not fix all the vulnerabilities as it comes by. So they collect all the vulnerabilities for a month and then fix that and then release the patch on the specific day. So it's for like the making the everyday life for the system operators, and then the vulnerability patchers so I can make their life easier. And then many companies, they have their own schedule. And then the reason why Patch Tuesday is important and then famous is that Microsoft products, they are like penetrated the market very well. And then their patch schedule is like the every second Tuesday of the every month. So I believe that you have, if you are using Windows, you have seen that like you need a Windows update or restart. And then I know that many of students and then even myself don't restart the computers for several months or something. And then because I have a lot of tabs open, a lot of applications open, I don't want to restart. But many people who don't study computer science, and then even for like someone who study computer science, don't know about the Patch Tuesday, and then complaining about the Windows always asking me to update. So that's not true. They will ask update every. So there's a specific time. I believe it's either 2 p.m. or 5 p.m. I'm not sure it's based on the Pacific time or Eastern time. So there's a specific time that the Windows release the patch on every second Tuesday. So make sure that Windows is not bugging you for update every day, so that they will ask you starting from Patch Tuesday, and then if you don't update that, it will ask you every day. Yeah, but the implication is that the Patch Tuesday will provide a lot of the good security things to your computer machines. So please don't miss that. And then if you have like this kind of the update request, then please do so. That actually reduce the opportunities to get hacked a lot. All right, this is the end of the part of the today. And then I believe like so I didn't bring the tutorial for the solving the buffer overflow challenge, but if you follow the content in the slide, then you can easily work with the buffer overflow challenges and then get the 2 of the flags. And then like I will stay here for 10 more minutes, so feel free to come down here to ask more questions. And then and don't forget, we have a quiz 2 on next Tuesday.
My SSH key got messed up or something.
Yeah.
Because it's requiring me a password when I try and log into the CTS server.